So now just going to have a look at how we actually do grammars in practice. So this is moving beyond talking about abstract grammars, so all possible grammars, and trying to think about how we talk about particular grammars, so the actual grammars that we're working with. So when you're writing a compiler and you have to write a grammar, how do you do that? So within Chomsky's hierarchy, we've got these various types of grammar of varying power and varying complexity of implementation. But the two that we're actually mainly concerned with are the simplest type 3 regular languages, which is regular expressions, and type 2 context-free languages, which we generally think of as sort of parser or grammar languages, especially the sort of simple nested type languages that we work with in general. And the two real-world things associated with those are regular expressions for type 3 and EBNF for type 2. I'm going to talk about these as if they are a standardized thing, but they're not really. So there's various dialects of regular expressions with different properties, but there is a core subset of things that actually are shared across all of them. And for even BNF, there's things like bison and yak that deal with BNF, but there's no hard and fast formal definition of exactly what those things are. You have to look at the documentation of the individual tools a little bit. So looking at EBNF, EBNF is a way of creating the right-hand side of a grammar more easily and more concisely. So on the left-hand side, we're going to still have a symbol that we're defining, while on the right-hand side, we're trying to build more complex things and more human understandable things. So the first thing that we add beyond just classic sort of formal grammars is this alternation thing, where we say A pipe B to mean either A will appear in the derivation or B will appear in the derivation. And it's either or. It's not neither A nor B can appear, or A and B can appear. It's sort of like an exclusive or kind of alternation kind of thing. Alternation is the equivalent to writing two rules in a formal grammar, except here you can just move both of them into a single definition. Clean star is a way of dealing with multiple instances of a particular symbol. So here we've got A star. And what this means is that where you see A star, there could be 1A, or there could be 2A's, or there could be 10A's, or there could actually be 0A's. None of them appear at all. Clean cross is slightly different. Here it says that for A plus, A must appear at least once, but it could then appear sort of 2, 3, 4, 5, 6, 7, however many times you want. So it's quite a subtle difference between those two things. The clean star can match nothing, but the clean cross must match at least one A. The optional syntax is another construct you see in a lot of different EBNF and regular expression grammars. So this is saying either A appears 0 times or A appears exactly once. So using those definitions, I can say, well, here is the definition of a thing called X. This colon equals is usually used as sort of shorthand for BNF, although again conventions vary a bit. But by putting this, it usually indicates that we're beyond the formal grammar world where we use an arrow. So we're defining what this left-hand side can be, and the first thing you see is we've got two pipes here, which means that there's actually, this is one possible derivation, this is another possible derivation, and this is another possible derivation. So rather than using three rules or three production rules in a formal grammar, we've got one single rule with three alternatives. Looking at the definition of the thing, well, one possible derivation of X is A. So that will match this case where X is simply the single character A. If we consider this B, then we would first try the A alternative. That doesn't match. We can try the B alternative, and in this case there is one B, which means that it matches B plus. There's no more B's, but that's okay, because one B is sufficient for this whole thing to match. looking at this production is going to correspond to this or this. We look for x and we say, well, this production, this derivation has to start with C. Okay, this one starts with C. Then once we've got our C, we look at the next thing, but actually the next thing comes back into itself. So now we're looking for another derivation of x, and one of the derivations of x is b. And actually we can now take that as the second part, and this whole thing matches this whole thing. So EBNF is quite convenient. Humans quite like using it because it makes the rules look prettier and easier to understand. But you can mechanically turn EBNF or BNF into the sort of more formal basic version where you don't have these nice conveniences. So here I've got a x being defined and it is using EBNF, but actually this is the equivalent or an equivalent, because there's no fixed equivalent. It's an equivalent to this. It should match the same things as long as I got it correct. So this whole EBNF thing is syntactic sugar. It's layers of stuff on top that just makes it easier for us to deal with. But the actual underlying power of this EBNF is precisely the same as the power of the formal grammar. So if we look at the way that we expand these things, the easier one to deal with is alternation. So if x can be either a or b plus, that's equivalent to having two rules, each of which define x, and they give one derivation each. So whenever you see pipes, you can just imagine there's going to be another line, and you put each alternate on the right hand side. The b plus, it's slightly more complicated, and something that's different here is we've had to introduce a new non-terminal. So by going from the EBNF version, we've had to actually expand the grammar slightly to accommodate this syntactic sugar. But this b prime here is actually the same as b plus. So it's saying, well, b prime is one of the derivations of x, and b prime can either be a single b followed by b prime, and that can go round for as many times as you want, or b prime can be b. And if you think of the derivations, that means that b prime here could be a single b, or it could be multiple b's. So that meets our definition of b plus. So the purpose of using EBNF is actually to make our definition simpler. So this is the definition of our toy example using EBNF, and you can see that rather than using 4 rules, we've got a single rule for expert and a single rule for opper, and all we've done is we've taken the right hand sides and put them either side of the pipe. But I think you would agree that this is actually a cleaner syntax, and it's nice to only have a single definition on the left hand side of expert. You're not limited to this in EBNF, so you can still define multiple rules for expert, depending on the tool. But it's easier to think about multiple alternatives on the right hand side. And generally it's nice, yeah, you should try to have one definition. Here's an alternative definition, an alternative grammar using EBNF, and this is meant to recognize comma separated values where the values are binary strings. So here's an example of where the clean star is important, because what this clean star is saying is that either you can have a value just by itself with no comma, or if you have a comma, that comma always has to be followed by a value. So you could have 0 of these and that would be fine, you just have a value. You could have 1 of these, in which case you have value, comma, value. Or you could have more of these, in which case you have value, comma, value, comma, value, comma, value. There's always going to start with a value, and it's always going to finish with a value, and there'll always be a comma between each of the values. So this is something that's more difficult to actually, if you try and do this using plus, is it possible? It is, but you have to introduce other non-terminals, I think. As we discussed in class, I sort of left in this thing, well, if we're going to define things that way, clearly the intent is that value is non-empty, because otherwise why care about this times? Why not just say that it could be comma or value, or if we're trying to be precise, why do that? So this we'd want to be careful about and think, well, is that actually what I meant? Did I mean this to be asterisk? Because if it's asterisk or clean star, then that means that value can be nothing. And that means that actually this thing could be nothing, comma, nothing, which doesn't seem like that's what we intended. It might be, but that doesn't feel right. So this is a case where probably this grammar is underspecified, and probably this should be a plus to indicate that a value cannot be empty. But it's up to whoever's defining the grammar. So a key thing to notice here is that these different symbols can appear as part of the EBNF's language, or they can appear as part of the language being defined. In one case here, these are being used as part of EBNF. These are not part of the language that's being defined. They are part of the instructions being given to the parser generator or whatever it is. So none of these things match characters in the actual input data. On the other hand, things within quotes do appear in the actual input language. So here we've got various literals, and these will actually match. So this matches an X that appears in the sequence of input characters we're going to parse. And sometimes the same character can appear. So here is bracket in quotes, here is bracket not in quotes. This one is matching a bracket in the language we're defining. This is a bracket being used for grouping in the EBNF. So you need to be careful about which one are you trying to specify. And generally quotes are used for literals, so they should stand out. And a good syntax highlighting editor will actually show you what the literals are. So here's a slightly more realistic grammar. It's still not massively complicated, but it looks a bit more like C. So now we have a sort of larger top level non-terminal, and so this would probably be the start non-terminal, start symbol of your grammar. And here I'm being, I guess, flexible and saying that the program can consist of 0 statements, 1 statements, or many statements. You might say maybe this should be plus. A program must always contain a statement, but that would be a decision on the part of the implementer. So going through, you can start to see the sort of the niceness of these pipe things, that now it's very clear that an expression is either an identifier, or it's a number, or it's one of these more composite things. But it's all in the same place, so I can actually see it quite easily. Where EBNF starts to break down is with things like this, where in order to specify what a digit is, I would have to list every possible alternative. So the literal 0, the literal 1, the literal 2, the literal 3. And this is why we often have a split between the grammar, which is in EBNF, which deals with tokens, and the lecture, which deals with regular expressions, that deals with characters. So the definition of a digit, actually the definition of a number, these are things that will more naturally be dealt with in a lecture. Similarly, this is probably something that would be dealt with in a lecture. It's slightly too low level. Grammars want to deal with tokens and words, not with individual characters from the input stream.